Hello, I'm Beomsu, a master's student from Interaction Laboratory at Posttech, South Korea. My research topic is image-based texture styling for motion effect rendering. A motion platform provides the vestibular stimuli that elicit the sensations of self-motion and thereby improves the immersiveness. The motion platform technology is now widely used for various entertainment purposes, including amusement rides and 4D films. A representative example is 4D Ride, which presents a video of POV shots and motion effects synchronized with the camera motion in the video. Previous research efforts resulted in a few automatic motion effect synthesis algorithms for POV shots. For example, Lee et al. Termed the motion effects for POV shots as fast camera motion effects and developed an automatic synthesis algorithms for them. Although effective in generating gross motion effect synthesis algorithms for POV shots do not consider fine features on the ground, such as a rough or bumpy road. In contrast, manually designed motion effects express such details by high-frequency add-in, eliciting sensations of roughness or bumpiness. The absence of such high-frequency texture signal can degrade the immersiveness and realism of the applications. In this paper, we propose an algorithm for styling the gross motion effects using a texture image. Our algorithm transforms a texture image into a high-frequency textural motion and uses the texture signal to stylize a fast camera motion and add details. Our algorithm takes a texture image, a camera speed, and a pre-generated fast camera motion effects, and then generates a stylized motion command through 3 steps: style motion effect synthesis, compensation of style motion effect, and merging fast camera motion effect and style motion effect. In the first step, a style motion effect is synthesized from the 2D texture image input and the camera speed estimated from the video. To generate a texture signal that preserves the spectral content of the input image, we apply linear predictive coding to the individual rows and columns of the image and obtain a large number of predictive filters. A texture model is generated by using the average predictive filter, and we synthesize the texture signals using the average prediction filters. We map the texture signals in the horizontal and vertical direction to the motion commands in the row and heap channels respectively. In real situations, a vehicle running on the road will shake more frequently and violently if its speed increases. This is reflected in the final style motion by resampling the texture signal in the time domain and scaling it as to the camera motion velocity. After scaling and resampling the texture signals, we can get the style motion from the 2D texture image. The second step aims to compensate the effect of the fast camera motion on the perceived magnitude of the style motion. In this step, the perceived magnitude of the style motion affected by the fast camera motion is equalized to the perceived magnitude of the compensated style motion when it is presented alone. We performed a perceptual experiment to obtain the perceived magnitude function of high-frequency motion stimuli when mixed with low-frequency motion stimuli. Then, we adjust the amplitude of the style motion effects in response to the amplitude of low-frequency fast camera motion. In the third step, the style motion effect is merged with the fast camera motion effect by model predictive control. As you can see in the upper plot, simple addition of style motion and fast camera motion can exceed the limits of the motion platform. MPC can combine 2 motion effects such that the merged motion fits into the motion platform's workspace. We also integrate the vestibular perception models into MPC so that it preserves the perceived angular velocity and the perceived linear acceleration. To evaluate the effectiveness of our texture styling algorithm, we conducted a summative user study. Participants experienced combinations of audiovisual content and motion effects. One was commercial effects manually designed by experts. Other one was motion effects generated by the fast camera algorithm by Lee et al. The other two were our texture-styled fast camera algorithm with or without the compensation, which was the second step of our algorithm. Then, participants rated 6 subjective metrics: enjoyment, immersiveness, realism, fatigue, harmony, and preference. We used 3 commercial 4D ride films purchased from CJ 4Dplex. These videos were chosen for the diversity of the floor surfaces in the videos. All of the 3 films were cut into 20 seconds clips where the ground texture was well seen. The texture images for each video were also selected differently to fit with the video content. The 2 motion effects of our algorithm showed better performance than the fast camera motion for most metrics. This result supports that our approach is successful for enhancing viewer experiences. However, the motion effects of our algorithm could not outperform the manually designed one. In Video China, the 2 textured automatic effects showed better scores than the fast camera motion effect, but with no significant differences. It can be due to this Video China accompanying the most dynamic and strong motion effects than the other videos, as commented by 5 participants. This could have made the viewer experiences enhanced by the addition of the texture motion effects less contrasting. In Video Rail, our algorithm significantly outperformed the fast camera motion for most metrics. This evidence supports the benefit of texture styling of motion effects. According to the participants' interviews, the lacking in bumpiness in the fast camera motion caused the sense of speed to decrease. Also, 2 of participants said that the up-down shake of our algorithm's result elicited more immersive experiences. However, the continuous and stronger shake in our algorithm could feel unrealistic and cause more fatigue, also as commented by the 3 people. In Video Race, none of the motion effects had a significant difference. It can be because Race used the smoothest texture image. Interestingly, 7 people reported that the bumpiness of manually designed motion was inadequate for the video since the racing car ran on the clean asphalt road. The proposed algorithm has several advantages. First, texture styling can be done easily with only a single texture image. Second, a perception model for high-frequency motion is explored when it is presented with gross low-frequency motion. Third, MPC used for merging low and high-frequency motion effects well respect the motion chair's working range while preserving the perceived angular velocity and linear acceleration. Finally, the effectiveness of our algorithm has been verified by users. Thank you for watching, and please check out our paper for more details.